very little bit of what's in that Shellcoder's handbook, which is quite an advanced book. Now, our direction we're going to do Linux and Windows, but we don't have enough time, so we're just going to exploit some measures. Anyway, the basic concept is in an application has a flaw of some kind, you use it to take over the machine, or do something you shouldn't do that. We're going to do the simplest thing here, and just first you're going to bypass a product key. And if you finish that, I already finished. Generally, you find these things with fuzzing, where you send just a lot of random packets to a service to make it crash. And after you've created a denial service, you then try to capture it and turn it into low code execution. So instead of just trying to execute invalid instruction dying, it executes the instructions re-injected, and then you gain control of the machine. So in order for this to work, it all works by exploiting the layout of memory. So the fundamental script here is always the same. It is taking the computer and missing one kind of data as another kind of data. You put in something that's supposed to be just static data, like an image or text, and you convince the computer to execute that stuff as instructions. That's the trick. And that leads to a few problems, but that's what makes it possible. Now, when I started in the old days to make this processes, there was no memory management at all. I wrote self-modifying code all the time. But you can't write self-modifying code anymore. Because the text section is where the instructions are to read over. You're not allowed to alter the instructions during the execution of code. But you can alter the data and the DSS section. The stack is the main thing, the simplest thing to exploit. That's what we're going to do today. You can exploit everything to the easiest one. Because the whole entire purpose of the stack is so one routine can call a subroutine and then return one. And the step where it returns is the dangerous part. Because when it's in the main program and you call the subroutine, it has to save its current state. So it pushes a bunch of things onto the stack, including the extended instruction part, and creates a new stack frame so the subroutine will have its own local variables in the stack. And then when it's done, it has to pop all that stuff off the stack, including the instruction pointer where I left off. And therefore, you can mess with the local variables in the subroutine, override the stack, change the instruction pointer, and when it tries to return from a function, it will accidentally return to the wrong place and execute the code you injected. And that's the classic way to overcome the exploit the stack. You can do the same thing with heap, but it's more difficult because the heap is a more chaotic place. And anyway, here's a nice diagram of the Linux layout of the RAM. You see the kernel up here, which is the direct connection to the hardware. You're not allowed to talk directly to the hardware. Instead, you have to ask the kernel to do it on your behalf, and you're stuck with whatever it is in the kernel. Then you have the stack going down here, another segment here, and keep going up here, and then down here another segment, down here with instructions. So you can't change the instructions, but you can mess with the stack and make one stack frame lead into the neighboring stack frame, and that's enough to give you control of the machine in the simplest case. So to do this, you have to know a little bit of assembly. You don't have to know much to do it. In simple cases, the more simple you know, the better. So one thing there are a lot of different versions of assembly out there. The most common type, and some are going to work with x86, is 32-bit code. Most attacks are written in 32-bit because you can run it on 32-bit machines. But nowadays people write with other architectures like ARM and such, and that's fine, but you can get them tools for it. So assembly, you have simple mnemonic, and then you have the argument. So then you can move the standard key register 42, that's backwards, and just because we're not making sense of this, that should be this way, that comes in. We'll get there in a minute. That's a Windows spec command. Anyway, the point is you can have fixed values like 42, you can have registers, or you can have memory addresses where you're putting in brackets, and that's pointing. So EAX is taken as an address, and the frame to memory location is pointing to it. You have a lot of registers in the modern instruction manual. I started with nothing but add. Anyway, now there's all these registers, very temporary values called grid calculations. Here's the bottom of the current stack frame and the top of the current stack frame, so to say, for execution. And here's the extended instruction point, which is mainly our target when trying to do very simple exploitations like what we're going to do today. We want to gain control of that. That's your obvious way to change the code of code. So simple instructions, move source to destination. That's the AT&T format used by Linux developers. Just to make sure that we all have enough headaches in our life, Windows does it backwards. We move the source to destination, and the mnemonics are a little bit different too. So you have these two different things both in common use. In Linux you use this one, and Windows you use that one, and you have to know both. But today we're just going to exploit Linux. Right. So one thing you might like, if you teach a second language, I was very pleased to find this product in Germany, a Java-based simulator, which is much better than anything I've seen before to teach people basic instructions, because it has pretty much everything the Intel processor has. And then you can just look code here at the one. So I got a couple of projects on the page. Let me point you to these projects. I'll just quickly discuss the first couple. So go to Info, is up there on the board. And the second event here is exploit development. So I have 4 projects here you can do. The simplest one is Jasmine, where you run this simulator, and you can just see how it goes. You got registers up here, you got flags here, you put your code there, and you have memory here. This is incredibly simple. The stack is here and goes down, and all these locations are at the bottom and come up. The play with some stuff here. You can put in some very simple programs like this, UVA, for listing, because the Jasmine does it. You have a run, stop, and reset button to run your code. You can single step through code. Your code is just plain text files, you can save it in Notepad and all that jazz. So this is great for students to learn simple. I've had a lot of people that take this class, that's all they care about. That's all they want to go in their classes get. Anyway, that's one thing you might take a look at. But if you want to actually exploit something and you're not worried about learning simple, then you may want to go on to the debugger overflow. So this is all based on Alice Lunch, a regional staff article that started it also most of us. The publicized a technique that you put runs underground for a while. Matching the stack to common product. And the point here is you have to overflow a buffer. And so there are 2 projects where you do it. The first one is here. Linux buffer overflow without shellcode. This is the simplest one that I could find, the simplest project. The first thing I do is downgrade my Linux to the very old, well not this one, this is going to be down here. Because what we're going to do here, we're going to exploit a simple program. I wrote a simple program here which just asks for passwords like a product. This is really old school hacking where you have some program ask you something annoying like a password or product key you don't have and you want to get that. So down here, there's fail and win. I want to get to this. So even though I don't know the right passkey, the only reason I don't know it's nonsense here, I just put some bits to make it so the password is just not sitting there reading. So it's not obvious what the right password is. And so we're going to ignore the fact that it asks for a password and tricking and telling us we're getting it. Just like you might jump over the product. So compile that thing, and when you run it, you will see, if you look at the code up here, I only set aside 10 characters for the password, but I did not actually limit it. So I can't put in more than 10 characters. And if I do, you will overflow it, and you can see that here, you put in 40 characters, you get a segmentation point. Because the canary hits the catch word. Now, to debug it, you can use Debugger. This is what everyone uses. It is a user hostile program. But it will only do a few simple commands here. Now, in this case, we compiled it, keeping the source code in there, which is kind of cheap. Your malware authors will not be that kindly, but we can be that kind for starters. So you can actually list the source code and put breakpoints right in the source code, which makes it more friendly. So I list one itself to see all the source code in the debugger. And then I put a breakpoint at 8 and a breakpoint at 10. So it's going to break before it's reading the string, and it's going to break at 10 before it returns. So I can see what's happened. Before I read the string, I can look. After I read the string, I can look and see what damage has been done by putting in too long a string. So if you run this thing and look at the registers, you'll see the ESP here at 4E0, EGP at 4E8. So this is the stack pointer of the current stack. And this is the beginning of the next frame, 48, so I'm jumping into a subroutine. And then there's EIP down here, which tells you where we are. And you can examine the stack frame at this. This is examine 20 words hexadecimal, which just dumps them out in hex here. And the highlighted portion here is the current stack frame. So I'm jumping into a subroutine, which is tested for the password. And in browsing the subroutine, these are the local variables. And when it comes back, this is the EIP. It's going to be popped off the stack and resume where I left off. So my trick is to find how many local variables I can overflow and change that number, and then I can overflow the variable. It's the very simplest case for buffer overflow. So if you overflow the stack with 40 characters, you usually choose some kind of simple pattern. like AABBCC, because it's usually spotted in text. So now I just run ahead to the next breakpoint, and when I look at the same stuff here, now I see, here's the A. A is 41, B is 42, C is 43, and on it goes. Here's all my characters. One annoying thing is characters going from the right to the left of each byte, so you have to deal with that. But anyway, you can see, I've got 50 and 51 is what it'll focus back. And that's, I think, P and Q. So I have located what part of my task does that. So I can now move forward a bit, run to where it crashes, look at the registers and verify that EIC does become 50, 50, 51, 51. And that's what I want. So all I have to do is put the right characters in. Now, to choose what to put in there, I can disassemble my main and look at the assembly language. That's why I say you really don't need to know a lot of assembly language to do it. If you disassemble main and just look at it, you can kind of remember how the C was. It's going to jump to a subroutine, input some password that's going to return whether like a 1 if it was the right password, and 0 if it's the wrong password, and if 1 it prints fail, if it's 0 it prints Google, something like that. So I look at this thing, it's going to call test password here. It's going to come back and do some kind of comparison whether EX is 0 or not. If it's equal, it's going to go down here. If it's not equal, it's going to go here. Here it's going to call putS and print out a message. Here it's going to call putS and print out a message. So the first message is fail, and the second message is succeed. So where I want to jump to is here, where it will not do the test. It will be in the subroutine and return to here, skipping over those steps. And then I'll get the win message. That's the plan. All I really had to do is get this value here, 84B50D. And I have to put that in instead of the P's and Q's. And so, yeah, here's the right exploit. That value back at 84850D. That's the hexadecimal values that go here. And in this case, I probably could have gotten away with just using the print here and having it put a carriage return at the end, but it's a poor practice. This is how you actually call out exactly the characters you want without a carriage return at the end, because that sometimes will hurt you. So this is a simple Python script that will create that text file. And if you try to print it, it will not print correctly, because those characters, these hex codes will turn into IDs and overwrites and nonsense like that. But anyway, you can put it in a file, and you can run that file. One thing that you will have technically a lot when you do exploit development, proxy with this simple thing that's all ready to go, is you will make mistakes. It's very hard to get it right. So you test it in the debugger first, so you can see what really happens. One thing it took you a while to learn, because VDB is not fun to learn, is how to put arguments in the command line here. You can run it here, and put in a breakpoint before it returns, and here's how you run it with arguments. Run --r is attack.tw, so it's going to feed that text file into it and make it crash. And so now I can look at the stack here, ready to go, with the 50D here, and you see what it did work. Here's the A's, and G's, and C's, and D's, and E's, and all that jazz. And down here, that's that number, 0804E50D. So it is right, and it should work. So if you go forward, now it prints new width. Then it crashes, because the stack is not set up correctly, but I don't really care. I've defeated in by changing the distribution of the program. If it works in the debugger, that does not mean it will work in real life. The debugger is not perfect. It has defects. Often the addresses are wrong. This is one of the reasons why I often need a not sled. But in this case, it has to work in such a simple attack here. So that's the one you should start out doing, that one, or jazzing, and I'll just go around and help people. And if people are making progress on this one, I'll talk a bit about the next one where you do privilege desperation, which has a little more advanced shelter. Try some of that stuff. You've got a calibration machine to do this stuff, and you can have that, and then you can do the power calling while you're working on this. we turn it like 15 minutes left. Look, I want to talk about the one we did not get to, the one which point out 3 more things here. This is the last project from the 4 I put there. Linux buffer overflow with the shellcode. And this has a very simple shellcode, but there's a couple more things. The first thing is there's a bunch of dependencies you have to turn on to do this kind of exploit. Other space layout minimization, doing things randomly in memory, it makes this kind of exploit very difficult. So you can turn it off. If you do here, you have a little program that will show you the current stack pointer, and if you run it 3 times, you get random numbers every time. Because it's moving. Every time you run it, it's random. You turn that off in this kernel variable, and after that, every time you run, you get the same answer. So that's taking the fact that old-fashioned, but it's easy to exploit for starters. And then bringing in the vulnerable program here, all it does is have a buffer and copy something into the buffer. You need more than 10 or 20 characters for a reasonable exploit. You need something like 100 or 200 at least to really be fun. So this time make the buffer 100. And when you compile it, you turn off the stack protector and the non-execute permission of the stack. All these are the way things were in the early days. And then, when you put in 116 A's with a lower quarter stack, and you give you the segmentation clause. So the trick here is I'm not going to jump to another part of this code, I'm going to inject my own code and run it. And for that, what I did here was you run the thing, go to the breakpoint, and you can see the stacks in it as you did before. Here's the A I put in for 1 character with a variable start, and here's the extended instruction point. So the trick here is I'm going to inject the A, then I'm going to inject shellcode in here, then I'm going to change the instruction pointer to point back inside there and run the code I stuck in. So the code has to fit in within 100 bytes. So that's beginning here. If you fill it with a lot of A's, you'll see all these A's here, and some of them overflow the EIP. That means it's going to work. So then you have to get an exploit. Now I just went on web and got an exploit. If you go in the extra project, we'll show you how to make your own with Metasploit. But here's a very simple one, it's only about 30 bytes long. And this is a privileged exploit exploit. It opens a dash shell. You can get it with the administrator. But it doesn't do anything in Kali Linux because you're already administrator, but at least it's something you can see. And it's only 32 bytes long. You usually have to have a notch sled before it. So your exploits will actually look like this in the code. You put in a bunch of 90s, which is nothing. Then you put in those 16 bytes. Then you have some A's to pad it. And then I put here B, C, D, and E, which is where I'm planning to change the instruction point, just to make sure I can get it. So all I have to do is guess approximately the address. As long as I get anywhere in the notch sled, it'll be fine. It'll be nothing, and then I exploit. And that becomes really important when you go exploiting Windows. You always need to have at least a 16-byte notch thread, or nothing you get from Metasploit will work. Just uses the first 16 bytes as a scratch pad, one of the nasty functions. Anyway, so that is the V4 is the final attack. You make it in the simple thing here. You have 64 90s, you have the shellcode, then you have some padding, and then you have extended instruction pointer pointing here. And what I did was just look here and pick an area in the middle of these 90s. I picked that's 450, just to get somewhere in the 90s. And that works. Then, when you run it, you change your prompt to a pound. So that's the dash shell instead of the bash shell, and that was the goal. Now, you may have noticed that everything we're doing here is useless. If you want to actually do real exploits to do fun things, you can go to more projects here, and even these very simple attacks will still take over modern versions of Windows, like Server 2012, if you want old code. So here's with a vulnerable server on Windows 7, you can put on the server style dependency in 2012 and have stopped it, and then you can exploit it with return on every code. So you can overcome all the modern defenses with a few additions to this, but you have to learn Windows-based debugger and such. So the big tool there is Mona. Mona is very really Python stuff, but really saves you a lot of bother here. So this is just the first step. There's about 3 more steps before you really can go with modern versions of Windows, but it's not impossible anymore. If you run old code on Windows. Anyway, well, this is a lot of